Welcome students. Here we are going to apply what we have studied in our last video. In the last video, we have obtained an expression for what? We have obtained an expression for the electrical field. That is, E vector is equal to 1 by 4 pi epsilon 0 integral of dq divided by r square into r cap for continuous charge distribution. Using this, we are going to study about three cases. Case number one is linear charge distribution. What do you mean by this linear charge distribution? Let us consider here. I am taking a long conductor or an uniformly linear conductor or a long conductor, and this long conductor is positively charged. The charges available in this conductor is uniformly distributed over its length. Let us take the length of this conductor as L. The total charge that was being available in this conductor, we are taking it as Q, or I can take it as plus Q. Now, what I am going to consider, I am taking a point P here. Due to this distribution of charges in this conductor, what is the net electrical field E vector at this point P? For that, what I have to do? For that, what I have to do is, the first concept is, I have to consider a small length in this conductor. So, that small length in this conductor, let us take that small length as dl. Let us take this small length as what? This small length as dl. In this small length dl, let us take the charge available as dq. For the small, infinite small length dl, instead of L, the whole length is L. I am taking this small length I am taking it as dl. In this small length dl, the charge available is dq. From this center of this dl, I am drawing a line from that point to the point P. This distance, I am considering it as r. If so, how I can able to calculate this electrical field? So, let us consider a small description. The total charge available is how much? I have taken it as plus Q. So, I am writing here the total charge, the total charge in the conductor. The total charge in the conductor, according to your book, the total charge in the conductor is given as a capital Q with the positive charge. So, I am converting here also as plus capital Q. What is the total length? Then the next step, the total length is the total length of the conductor. Total length of the conductor. The total length of the conductor in your book, it is given as capital L. Okay, then I have to change this as capital L. Okay. Now, we have to calculate first of all linear charge density. What do you mean by this linear charge density? Linear charge density means charge that is available per unit length. In 1 meter length, what is the amount of charge available? That is linear charge density represented by the letter lambda. If you want the definition, you can study the definition like this: charge per unit length. Charge per unit length. So here the total charge available is Q. The total length available is L. So in 1 meter length, the charge available is lambda, that is Q divided by L. If lambda is equal to, therefore I can write lambda equal to Q divided by L, then this is measured in terms of Q in terms of coulomb, L in terms of meter. So coulomb meter is its SI unit. So this is the SI unit, but I am in need of only this value because for 1 meter length, if I am considering what is the value of the charge? I can calculate the charge for any length. Then, you might have, we can see it with the help of an example. You are going to a shop. You want to get some 5 pencils. But you are going and asking how many number of pencils are available in a box. They are saying the total number of pencils in the box is 10. You are asking what is the cost. The cost of the 10 pencils, they are saying it is 100 rupees. Then you can calculate what is the amount of or what is the cost for 5 pencils. It is 50 rupees because you will be calculating the cost for 1 pencil and then you will be multiplying it with the number of the cost for the number of pencils. From that you can calculate the total amount you have to pay for that 5 pencils. The same concept here. The total length is L. In that total length, the total amount of charge is Q. For unit length, that is for 1 meter length, how much amount of charge will be there? That is given by lambda. So lambda is equal to Q by L. Now what I am going to take? In this long conductor, I am going to consider only this small length dl. So consider, you write. So you consider an infinitesimal, infinite small. Now infinite small, what we are calling it out as infinitesimal length dl. Okay, infinite small length. How much length? That length is dl. See, in this length dl, how much is the amount of charge? And let us consider, let dq be the charge in that length, or dq be the charge present in it. dq be the charge present in it. Okay, let us write like this, charge in it. Now what I have to calculate? In this dl, if dq is the amount of charge, then what is the value of dq? See, I can substitute here. That is lambda equal to, instead of q, what I can write? Instead of q, I can write dq. So instead of L, I can write dl, because in dl the charge available is dq. Therefore, the total charge is dq is equal to, make a cross multiplication, you can able to get lambda into dl. This is the use of linear charge distribution. Now what you have to calculate? You have to calculate the electrical field at P due to this dq, and then when you are integrating it, you can able to get it for the whole length. Therefore, we can calculate the electrical field due to the line charge, due to the line of total charge, line of the total charge Q is linear charge or line charge. What is the total charge? Capital Q. If you want to calculate that capital Q, that is E vector, first of all I have to calculate dE vector for this dq, which should be integrated, which is equal to integral of, what is this, dE, 1 by 4 pi epsilon 0. We have calculated q by r square. Instead of q, I have to write dq divided by r square, multiply it with r cap. But you replace this dq with this value, what you can able to get now? See, I can write this as the electrical, therefore the electrical field E vector is equal to integral of 1 by 4 pi epsilon 0. What is that dq? See, we have calculated, or we have written dq here as lambda into dl divided by r square into r cap. Clear? See, if you are removing this r cap, then it is the magnitude. What is the direction? Direction is since the linear conductor is positive, since the linear conductor is positive, electrical field will act, electrical field at P will act away from the conductor, or away from the positively charged conductor, or we can write away from positively charged conductor. Clear? Purunjuda? So just to see again what I have dealt. See, for a linear conductor, okay, for a linear conductor, I have calculated the electrical field at this point. For that, I have taken a long conductor of length L. See the cursor, where the cursor is moving. And for that long conductor, the total charge is plus Q. Now, first point, I am calculating the linear charge density. Linear charge density is nothing but charge per unit length. See, charge per unit length is what? Charge per unit length is lambda. That is total charge by total length, assured in terms of coulomb per unit, coulomb per meter. That is its unit or the SI unit. Now, in this long conductor, you consider a small length dl. In that small length dl, the charge available is dq. So, I have written it. Consider an infinite small length dl. In that length dl, that small charge is considered to be dq. So, linear charge density lambda can be calculated as dl divided by what? dl divided by dq. In that case, I can calculate dq. What is dq? dq is equal to lambda by dl. Therefore, the electrical field due to the total charge is considered to be q. Total charge can be calculated as, for this dq, I have calculated dE. That dE is integrated. I can calculate total value. If you want to calculate the magnitude alone, you leave this R cap, then you can able to calculate. If you are leaving this R cap, then you will be getting the magnitude alone. If R cap is included, we have to say the direction. What is the direction? Since the total charge is positive, the electrical field will act away from that positive charge. Now let us go for case number 2. What is case number 2? See, what is this case number 2? In order to study about the case number 2, I am considering another charged body where the charges are distributed uniformly. Here, case number 2 is surface charge distribution. What is that surface charge distribution? Here we have to consider a plane surface where the charges are distributed. For a case one, linear charge. In a long conductor, the charge is distributed. Here we have to consider this as what? Here you have to consider a plain sheet of charge. So I have considered a sheet, a plain sheet. In this plain sheet, the original area or the total area, I am considering it as A. What is the total charge available? Like the previous one, I am considering the total charge available is dq. In this case also, the total charge is taken to be positive. The charges are distributed continuously inside this plain sheet of charge. Now, in this I am taking a small, infinitely small area, which I am taking it as dA. In that long conductor, charges are distributed linearly. In this plane conductor, charges are distributed over its surface. So it is called to be surface charge distribution. Now from this surface, I am considering a point. Let us take that point as P. If that is the case, from dA, the point P is at a distance of, let us take it out as R. What is the electrical field at this point? E vector. Due to this uniform distribution of charges in this plane sheet. How I can calculate? Again, here you consider. So let us take like that of the previous case. Same procedure you follow. Easily you can able to study the total charge in this case is considered to be equal to Q. Then total area of the plane sheet. Total area of plane sheet, or you can say plane sheet of charge. Let us consider it as capital A. Now in this case, as that of in last case, linear charge density. Here the charges are distributed on its surface. So you have to calculate surface charge density. What is that? Surface charge density. What is linear charge density? Charge per unit length. So surface charge density is charge per unit area. It is nothing but charge per unit area. Charge per unit area is represented by the letter sigma. What is the total charge? Total charge is Q. What is area? Area is A. What is its SI unit? You can write the SI unit. What is its SI unit? Is charge is measured in coulomb, area measured in meter square. So I can write coulomb per meter square as its SI unit. So we know the formula, sigma equal to what? Sigma equal to Q by A. As that of the previous case, consider a small area. Let infinite small area, infinite small or infinitesimally small area, which is considered to be dA. The charge available in it is the same procedure as in previous case. The charge present in that area, present in it, in this small area dA, let us consider it as dQ. If so, I can calculate what? If so, I can calculate surface charge density. What is the value of surface charge density? Therefore, I can write sigma equal to dQ divided by dA. Therefore, what will happen? dQ by dA means dQ. What is the value of dQ? Cross multiply. You can able to get sigma dA. From this, what you can calculate? From this, you can able to calculate dE. What is the dE vector? dE vector equal to the small electrical field at that point P. 1 by 4 pi epsilon 0 into dQ divided by R square into R cap, which can be written as, see, 1 by 4 pi epsilon 0 into, what is this dQ? It is sigma dA divided by, from here I have written sigma dA divided by R square into R cap. Again you see how I can simplify this. What is the net electrical field or the total electrical field? So I can calculate the total electric field at point P, at the point P, due to the total charge. Due to the total charge. What is that total charge? Q is total electrical field. I have to write it out as E vector. If I want to calculate total electrical field, I have to integrate. I have to integrate that small electrical field dE vector, which is integral of, what is this dE? I have written 1 divided by 4 pi epsilon 0 sigma into dA divided by R square into R cap. If you want to write the unit is Newton per coulomb, because we have calculated the electrical field. If you want to write the magnitude alone, leaving this R cap, you can get the electrical field. What is the direction? So, direction of electrical field is, field at P is acting, it is acting away from what? Acting away from the point, away from the charge or away from the plane sheet, away from plane sheet as it is positively charged, as it is positively charged. Clear? Purinjada? Let us go for the third case. The same concept. See, again you see, I have taken a plane sheet of charge. in that plane sheet the total charge is A, total charge is Q, and I have calculated what? I have calculated a small area dA. For that small area I have calculated this dQ, the charge available, from which dE is calculated. After calculating dE, by integrating that dE, I can able to take the total electrical field E. And the third case, what is the third case that we have to study? The third case that we have to study is volume charge distribution. So let us go for case number 3. Case number 3 is volume charge distribution. What do you mean by that? Volume charge distribution. The charges are distributed throughout its volume. That is volume charge distribution. See, in the first case, the charge is distributed lengthwise, linear wise. So linear charge distribution. In case number 2, the charge is distributed over its area. So it is surface charge distribution. And that case, we are going to consider the charges are distributed over its volume. That is called to be volume charge distribution. For that, I can consider a sphere, or I can say an uniformly shaped body, where the total volume of this body is V. Let us consider the total volume as V, and let us take the total charge available as Q. The same procedure let us follow. In this, you consider a small, infinitely small volume. Let it be dV. Consider a point P. So the distance from this small volume dV to the point P is R. I have to calculate the electrical field at this point P due to the whole volume V. Now, you consider the description as in the previous case. What we have written in the previous case. Let us consider like this. The total charge in the given volume. Total charge in the given volume is capital Q. Total volume of the body. Let us consider it as capital V. See, in lengthwise linear, we have calculated linear charge distribution. We have taken linear charge density. In area, we have calculated surface charge density. Similarly, here we will be calculating volume charge density. What is meant by this? Volume charge density. It is not given in your book, but you consider. That is rho. Volume charge density rho is charge per unit volume. Let us consider like this. Charge per unit volume. What is charge? Capital Q. What is volume? Capital V. What is the unit? Charge measured in coulomb, volume measured in meter cube. So coulomb per meter cube can be taken as its SI unit. This we are calling it out as its SI unit. Now, instead of taking this total charge or total volume, consider a small volume dV. Consider a small volume dV. See, the same procedure I am following as I have done in the previous cases. So it is easier for you to learn and write. In this small volume dV, let the charge present. Let the charge present be dQ. Therefore, volume charge density rho equal to dQ divided by dV. If so, I can say on cross multiplying dQ equal to rho into dV. So if rho into dV is calculated for dQ, I can calculate electrical field for this small volume. electrical field at P due to dq. I can write this as dE vector, which is 1 by 4 pi epsilon 0 small charges dq by r square into into r cap, isn't it? So into, I can write it out as r cap. See, this can be written as 1 by 4 pi epsilon 0. What is this dq? dq can be written as rho into dv divided by r square into r cap. Now I have to calculate the total or the net electrical field. So the net or the total electrical field at the point P due to the total charge Q, due to the total charge Q, which is distributed uniformly over its volume, is given by E vector is equal to 1. We can write, see, first of all you can simplify, you can write like this, see, integral of d vector, which is equal to integral of 1 by 4 pi epsilon 0 rho dv by r square into r cap. If you want to write the direction, how you can write? If you want, you can simplify this also. See, rho is considered to be constant, 1 by 4 pi epsilon 0 constant. So 1 divided by 4 pi epsilon 0 into rho into integral of dv divided by r square into r cap. If you are leaving that r cap, then you can say what? Then you can say it is a magnitude. If you want to write the direction, then I can write the direction is given by, the direction is always away from the charge, away from the charge or the charged body, since it is positive, since it is positive. See, in all these cases, since the charge is taken to be positive, the electrical field at the point will be always acting away. Instead of positive charge, if you are considering negative charge, then the direction of the charge will be towards that of the body or towards that of the parental charge, negative charge. I think you are very clear with this. You may be expecting this for a big question, 5-mark question. That is, explain generally the continuous charge distribution and obtain a general expression. After that, you may be asked to get expression for electrical field due to continuous charge distribution in the 3 cases, that is due to linear charge distribution, due to surface charge distribution, and due to volume charge distribution. See, while studying this, try to work it out along with what I have gone with. Along with me, you take a notebook and each and every step, write it in your book, and you just recall each and every previous step and go with the next step and try to study this derivation easily by writing it. Don't mug it out. You just write it out and write it out 2 or 3 times and do it simply. Okay, all the best. We will meet in the next video. Thank you.